So we looked at representing a function using geometric series as sort of the conduit to do that. That does eventually wear itself out. There are some functions for which it's just impossible to get there. So we talk about this last concept of Taylor and Maclaurin series to help us represent a function with a power series. And we would use this when we have a function that has derivatives of all orders. Now, what does that mean? It means you continuously take the derivative over and over and over and over again, and every derivative exists at x equals c. So think about some functions that are very easy to repetitively take the derivative, and all those derivatives will continually exist at a particular value. Sine is a good example. Cosine is a good example. E to the x is a good example. These are probably your most common ones you're going to come across. So that's the ones where we're going to see this Taylor-Maclaurin series work for it. So what it says is that we can build our power series through these derivatives. So if you think about a power series, so we have some function f of x, and we're trying to come up with its corresponding power series representation, an x minus c to the n. Now, if we know what the center needs to be, because the question will say, find the power series centered at 5 or at 0 or at 1, we'll know what c we're trying to work with. So the only thing we really need to come up with the power series expansion for is to figure out what the a sub n component would be, what those coefficients are all going to look like. Well, what this Taylor series and Maclaurin series say, and they're basically the same thing, it just depends on what the center is. The difference between a Taylor series and Maclaurin series is which center we choose. But the series have the same makeup in that a sub n component, that coefficient that we're looking for our representation, should have this form to it. Which if you look at f parentheses n, what does that stand for? That's the nth derivative of f at c over n factorial. So that a sub n piece should have that form to it over n factorial. So a sub 0 would be just the 0 derivative, which is the original function, over 0 factorial. A sub 1 would be the first derivative at c over 1 factorial. A sub 2 would be the second derivative at c over 2 factorial, etc. So all those coefficients will be based off of the derivative of the function that we're trying to represent as a power series. So this is what we call a Taylor series, a series that is made up of those components. And if we take that exact series makeup and center it specifically at 0, we'll call it a Maclaurin series. So generally, they're all Taylor series, no matter what the center is. And if the center specifically is centered at 0, then we'll call it a Maclaurin series. Again, this is all just about taking the derivative of the function and building a power series by repeatedly taking the derivative of a function and using this pattern. Again, f of c plus f prime of c, x minus c to the first, plus f double prime at c over 2 factorial x minus c to the second, etc. So the best way to see this in action is to do an example. So let's look at sine x, and let's find its Maclaurin series, specifically its power series, okay? But it's a power series centered at 0 if we're going to talk about Maclaurin. And we're going to also find its interval of convergence. So if we look at this, sine x does not have the a over 1 minus r field to it. It's not related to any function that has an a over 1 minus r field to it. So that whole concept we used previously of geometric series is not going to work. However, it is very easy to continuously take the derivative of sine x. So if I look at sine x, and I take the derivative of sine x, I get cosine x. And if I take the derivative again, I get minus sine x. If I take the derivative again, I get minus cosine x. If I take the derivative again, remember when you get to the fourth derivative with prime notation, that's when you start using those parentheses. I can't just say f fourth x. See, that's the fourth power. I have to put parentheses around it that tells me I'm using the fourth derivative. The fourth derivative gets me back down the sign again, and this whole pattern will just continue to repeat itself. And what I want to do is say, okay, I know those derivatives are going to keep going and going and going forever, and it's going to keep cycling back around the sign, and then eventually go, through this pattern again and again and again. How about if I look at those functions when x is 0? Because Maclaurin series, we have to be centered at 0. So f of 0, f prime of 0, f double prime of 0, f triple prime of 0, etc. Fourth derivative at 0, because that's where the pattern repeats. What do we get? Well, f of 0 would be sine of 0, which is 0. F prime of 0 would be cosine of 0, which is 1. Double prime at 0 would be 0. Triple prime at 0 would then be negative 1. And back to 0 again for fourth derivative. And this pattern will just repeat itself. 0, 1, 0, negative 1. 0, 1, 0, negative 1. And that's going to continue on. And that can go forever. So this function has derivatives of all order at x equals 0. Okay. So therefore, I should be able to come up with a power series representation that looks like this for sine x using Maclaurin series. So what are we going to do? Well, we're going to say that sine x should be equal to the sum of n equals 0 to infinity of the nth derivative at 0 over n factorial x to the n. Again, centered at 0. What is that really, though? What that is really is, if I plug 0 in for n, I would get f of 0 plus f prime at 0, x to the first, plus f double prime at 0 over 2 factorial x to the second. And there were factorials here, but this was 0 factorial and this was 1 factorial, both of which are just 1. Plus the third derivative at 0 over 3 factorial x to the third, plus the fourth derivative at 0 over 4 factorial x to the fourth, and that pattern just continues on forever. Well, what were these different derivatives and functions? F of 0 was 0, f prime of 0 was 1, f double prime of 0 was 0, f triple prime was negative 1, then 0, then the next one would be 1. That would be for the 5 factorial, and it's going to continue. So you see a pattern here. 0, 0, 0, they're all going to go away. What do we get? We get x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth. You see the pattern, minus 1 over 7 factorial x to the seventh plus 1 over 9 factorial x to the ninth minus, etc. So that is the power series for sine x. Now the only thing I have to do is I have to write this in summation notation so that I could figure out the exact power series centered at 0. So how can I do that? Well, let's see. Let's look at the sum of, say, n equals 0 to infinity of what? Well, these are all x to the 1, 3, 5, 7, 9. It's going to be x to an odd power. So let's say 2n plus 1. If I plug 0 in for n, that would give me x to the first to start with. Then if I plug 1, it would give me x to the third. Then if I plugged in 2, it would give me x to the fifth, etc. And if you notice that the denominator here, 1 factorial, 3 factorial, 5 factorial, is the same as the power. So let's say 2n plus 1 factorial. And the only other thing we need in this pattern is we have a plus, then a minus, then a plus, then a minus. So that'll be negative 1 to a power. Now we want that to start with a positive. So it's either going to be the nth power or the n plus 1 power. Well, remember, if we're starting with 0 as our starting index, if I say n equals 0, I want the first one to be positive, so I'm going to do negative 1 to the n. So now look at this. There is our power series for sine x. We didn't get there through geometric series. We got there through Maclaurin series, which is just about finding the derivative of our function repeatedly and seeing a pattern to those derivatives and building our coefficients off of those patterns using this nth derivative at 0 over n factorial as our coefficients there. The next part about this says determine the interval of convergence. Well, since we didn't go through geometric series, we don't have that idea of, oh, the absolute value of r is less than 1, let's use that. What we have to do is we basically have to come up with this interval of convergence really from scratch using this power series. Well, what we can do is we can use the ratio test. Go back to where we started. And in fact, one of the examples that we did was exactly this one. So I'm going to include that again right now. So cosine would basically work the same way. If I asked you to find a power series expansion for cosine, you could use Maclaurin, Taylor, depends on where you want to center it, but it would work a lot like the sine one did. Another good function that would work here would be e. In this case, this one is asking you to find the Taylor series expansion for e to the x centered at 1. I could really just say find the power series expansion for e to the x centered at 1, which is what we're doing. Taylor series is a power series, but by saying this, I'm kind of giving you a clue as to how to do it. But it doesn't necessarily need to be said. It could just say find the power series expansion. You would have to ask yourself, well, look at this function. How could I get this function to turn into or represent as a power series? First, I would ask myself is, does it have any relationship to a geometric series? Does it look like a function a over 1 minus r? No. E to the x does not. It's not related to anything in the form of a over 1 minus r, so geometric series is out. Next thing I would ask myself is, can I repeatedly take the derivative of e to the x, and would all those derivatives exist when x is 1? The answer to that would be yes. So then Taylor series is the way to go. And since we're centered at 1, this is Taylor, not Maclaurin. Taylor, remember, covers all of them, no matter what the center is. Maclaurin is if we specifically choose 1 as our center. So f of x equals e to the x should be equal to the power series, n equals 0 to infinity, of the nth derivative at 1 over n factorial times x minus 1 to the n. Again, because we're centering at 1, and we're plugging 1 into all the derivatives. So that's what the series should look like. In order to build this up, I need to look at the derivative of e to the x over and over again, which is just e to the x. I don't have to go very far to see that pattern. Okay, I don't have to go past really the third derivative. I think you see what's going to happen. Each one of those functions evaluated at 1 would be exactly the same thing. E to the 1, e to the 1, e to the 1, e to the 1. So then if I said, okay, well, what is this? Remember, when n equals 0, the 0th derivative is just the original function at 1 over 0 factorial x minus 1 to the 0. So if that's to the 0 power, we're not going to write that. So we just get f of 1 plus the first derivative at 1 over 1 factorial x minus 1 to the first, plus the second derivative at 1 over 2 factorial x minus 1 to the second, etc. So plug in what we know about all these derivatives. Well, f of 1, f prime of 1, f double prime of 1, they're all e. So this would be e over 0 factorial. Remember, 0 factorial is 1, so that's the whole thing would just be e, plus e over 1 factorial, that's also 1, times x minus 1, plus e, which is the second derivative, 1 over 2 factorial, x minus 1 to the second, plus e over 3 factorial, x minus 1 to the third. And that pattern is just going to continue on. If I wanted to write that in summation notation, Sometimes that's easier than other times. This one's not too bad. They all have an e in them. E is going to be over 0 factorial, 1 factorial, 2, 3, 4, 5, 6. So that'll be over n factorial. And I have this x minus 1 to the n for each one. Remember, this was x minus 1 to the 0, to the first, to the second, to the third. So that'll be to the n. So that is your power series centered at 1 for e to the x. Again, if I then wanted you to find the interval of convergence, the only way to do that would be to go back and use ratio test right now. Well, I should say the best way for you to do it right now would be to go back and use ratio test and find the interval of convergence. But that's the only time where this will equal this. This will have this representation is if we choose an x in the interval of convergence. Remember, specifically, the x that we could choose could always be the center at least. And we know the center is 1. So if I plug 1 in for x here and I plug 1 in for x here, that's going to tell me that this converges and this is what it converges to, which would make sense because thinking about this right here in expanded form looks like this. If x is 1, this is 0, this is 0, this is 0. So if all these are 0, what do we get? That. So here are some fairly common power series expansions for some functions that we are have some of which we've already seen. Sine x we did. Okay, this is the power series expansion for sine x. E to the x, well, we did it centered at 1. This is centered at 0. I gave you the example centered at 1 just so you saw an example centered at 1. Cosine x looks a lot like the sine in the way we do it. These are hyperbolic trigonometric functions. Probably not very familiar with those, so let's move on. Let's look at the log x one. We looked at that one earlier. 1 over 1 minus x is the one we started with. Arctan or inverse tan, we've already done that. So again, these are just some common ones. These are not the only ones, but there are quite a few power series expansions for different functions, and we've looked at some of the most common ways to get there. Geometric series or Taylor and Maclaurin series.